right, in this video, we're going to talk about the estimated standard error of the difference between independent means, which is a mouthful. It's the step we do after pooling the variance. So let's go back and review what we talked about in the last video. In order to calculate the t-ratio, we first need to pool the variance estimates from our two samples. So there's the term for the estimated pooled variance, and in the numerator, we simply have degrees of freedom for the first group multiplied by the population variance estimate for that first group or sample. We do the same thing for the second group or sample, and then we divide by the total number of subjects minus 2. And we need to pool the variance estimates in order to calculate the relevant standard error. And because we don't have any logical reason to prefer one variance estimate over the other, that's why we pool. So the formula creates a weighted average, which takes into account sample size by including degrees of freedom for each group. And you see that in the numerator. And the reason we weight the average is because larger samples create better estimates of the population variance. Okay, so then what's next? Well, we need to compute the relevant standard error, and it's going to take a little bit of an explanation for what the relevant standard error is. And let's just start with the observation that we have two samples in an independent groups or independent samples t-test. And that means that we have two means, one for each sample, right? So there's going to be a mean for sample 1 and a mean for sample 2. And of course, there's going to be a difference between the means for the two samples. So the question then becomes, how much of the difference between the means of the samples is simply due to sampling error, right? Because we don't want to conclude that there's a difference due to the independent variable when in fact sampling error could account for it. So if the difference between the means is more than what we would expect from sampling error, then we're going to reject the null hypothesis. Okay, so let's start off with an example. And in our example, we have two samples, and each sample would have a mean, right? So there would be a mean for the first sample and a mean for the second sample. Now, the first sample might be the group that received the manipulation of the independent variable. The second sample might be a control group, okay, just as an example. It doesn't have to be that way, but let's just go with that. Now, for each of these samples, we could run the experiment over and over and over again, right? Potentially infinitely. So each time we did that, we would get a mean for sample 1 and a mean for sample 2, right? If we ran it again, we get another mean for sample 1 and another mean for sample 2. And you'll notice that those means are not exactly equal to the prior mean, right? We wouldn't expect them to be. Okay, so that reflects sampling error, right? So the variation in those means for sample 1, right, is reflected in the difference in those values for the means. And we're making an estimate of the population parameter, the variance, the population variance. So we use this notation to show that we're making estimates of the population variance. Okay, same thing for sample 2. We have estimates of the population variance for sample 2, right? And so all these values are going to be different, each time we run the experiment. We don't expect them to be the same. Now, what that also implies is that there will be a difference between the means, and we get that difference by simply subtracting the mean for sample 2 from the mean for sample 1. So we might just subtract 3.50 from 4.50, right? We would subtract 3.40 from 4.35, or we would subtract 3.70 from 4.24. So we're going to get a difference when we do that. So in the first case, it's 1.0. In the second case, it's 0.95. In the third case, it's 0.54. Now, what you're noticing is that just like with sample 1 and sample 2, those values for the differences are not all the same, and nor should we expect that, right? So what we're creating is a new distribution, and it's a distribution of the difference between those independent means. And the variation in those differences reflects sampling error, but it's sampling error for the difference between the means of the two samples. Okay, but it does create a new distribution. Now, the standard deviation of this distribution is called the estimated standard error of the difference between independent means, which takes forever to say, okay? But it's notated with this notation, and that should make sense, right? Because right here we just have the difference between the means for the first group and the means for the second group. And then the S simply represents the standard deviation. And then the hat tells us that we're estimating that standard deviation in the population. But because we're dealing with means, we don't call it a standard deviation, we call it standard error. Okay, now to shorten things and make things a little less complicated, we typically don't refer to it by this big long term. We just get rid of the between independent means and we call it the estimated standard error of the difference. Now, here's an important note though about this distribution. The mean of the difference between the means, right? In other words, the mean of this distribution, if I were to average out all of these mean difference scores, that's going to always be equal to the difference between the population means represented by each of the samples, okay? So the mean of the difference between the independent means, that distribution, is equal to the mean difference in the population. And that's important because that's going to form the basis of our sampling distribution. So our formula for the estimated standard error of the difference is relatively simple. All we're going to do is we're going to take the square root of the pooled variance divided by n plus 1 plus the pooled variance divided by n plus 2. Now the n's just reflect the sample sizes for the groups. In most statistics textbooks, the examples you'll see will have equal n's between the groups, but that's not always the case. Okay? Good news is we've already calculated the pooled variance, right? The estimated pooled variance in the population. So we've already done that in the previous step. Now, if you really want to get kind of sophisticated, we can combine those two steps of pooling the variance and then calculating the standard error of the difference. That's going to lead to a really hairy looking formula. It's not that complicated, but if you just wanted to combine it all into one step, you'd use this formula. Okay, and what this will do is it'll both pool the variance and calculate the standard error of the difference all at one time. Now, my experience has been students like to do it in two steps rather than just one because it's easy to make a mistake entering the numbers when you have a huge formula like this. But either way, it doesn't matter. If you're good at calculations and you double check your work, this might be the more efficient way to do it. Okay, so from there, the next step is to calculate the t-ratio. Now, I like to use the term t obtained because when we say t-OBT, it's easy to distinguish between the obtained value, the t-ratio that we calculate based on the data from the experiment, and the critical value for t, which is what we're going to compare the t-ratio to and decide and use that to decide whether or not to reject the null hypothesis. So when you see OBT, all that means is this reflects the data that we've obtained and collected in the experiment. A lot of textbooks will just call it T, and that's fine. Either way, it means the same thing. So the obtained T, the t-ratio that we compute, is the difference between the mean for the first sample and the mean for the second sample, and then we subtract out the population mean minus for the first group minus the population mean for the second group. Now, in most cases, and again, this is true for most textbooks when you're running examples, the null hypothesis will state that the difference between the population means is going to be 0, right? The null hypothesis is going to say there's no effect of the independent variable, so we have no reason to think that in the population, the means will be different. Now, that's not always the case, and your textbook will probably talk about when that's not always the case. For example, there may be in the population a known difference between means, or there may be a parameter we want to put in there that essentially is an expectation of what we think the difference will be. But for the most part, we're going to enter in 0 there. So really what we have in the numerator is the sample mean from the second group being subtracted from the sample mean for the first group, and then we subtract out 0, which just means nothing in terms of the overall calculation, of course. And then in the denominator is our standard error of the difference. Okay, and that's how we get the t-ratio. All right, big picture. That wasn't so hard, was it? Big picture is this. The standard error of the difference between independent means, also called the standard error of the difference, is the amount we expect two sample means to differ from one another on average. So it's going to be our measure of standard error. The mean of the standard error of the difference is going to be equal to the average difference between the means in the population. And that's going to be useful when we form our sampling distribution. So really you have to just follow these 3 steps in order to do the t-ratio. First thing you got to do is you got to pool the variance estimates, right? And that was in the prior video. Second thing you've got to do is compute the standard error of the difference. And then the last thing that you do in terms of the calculation is to compute the t-ratio or t obtained. Now, once you've done that, you've got to make a decision. You still have to decide whether or not to reject or to fail to reject the null hypothesis, right? So you've got to compare that t-ratio to the critical value for t. Okay, now in the next video, we're actually going to walk through an example by hand to show you how to do this. We're going to go through all the steps, and really just remember, you just got to go through the same sequence when running these tests, and you should be just fine in terms of the calculations. Then after that, I'm going to have a video that shows you how to do it in a statistical processing program like JASP. And we also need to talk a little bit about calculation of effect size, because there's a couple of different ways to do that. But you're almost there. You're almost ready to start actually calculating the t-test for independent groups or independent samples.